All right, thanks so much for inviting me there, and I wish I could be there in person, but it's really hard. So I think I apologize in advance. Maybe for this crowd, the talk will be a bit too algebraic, but if something is confusing, please stop me and ask questions. So I'll try to go slow and not to be too algebraic. So this is a joint work with Andrei Neguts from MIT, and it's pretty fresh. So it's on archive already from last month. And so the main goal of this talk is to talk about this beautiful theorem of Morton and Samuelson, which relates the skein algebra of the two torus to some specialization of elliptical algebra. So I will define what is elliptical algebra in a couple of minutes. And this algebra depends on two variables, t and q. And so we just specialize t to be equal to q inverse. That's again some interesting algebra, and Morton and Samuelson proved that this algebra is actually isomorphic to some algebra that many people here care about, namely the skein algebra of the torus. So what is it? So the generators of this algebra are all possible links in two-dimensional torus cross interval, framed, oriented. The multiplication in the algebra is just taking of these links, the union of these links in the 0-1 direction. And then all this is taken modulo local skein relation. Whenever we see this kind of picture in the link in a small ball, and this kind of picture, we can relate them. And the difference is q minus q inverse times this thing. So just to repeat, the skein algebra depends on one variable q, as many people here know. This is what is called Homology PT skein algebra, to be specific. So this is not the Kaplan bracket skein algebra or anything like this. And then on the other side, you have some mysterious algebra, which I haven't defined. You specialize t is equal to q inverse, and then you recover the same thing as the skein algebra. And I will briefly explain the idea behind the proof of this theorem. But for most of the talk today, I want to talk about two things. So first of all, what is elliptical algebra and how to define it properly with two parameters q and t. And there are several definitions. They're all more or less equivalent, and the various presentations by different generators and relations. And I'll talk about at least two of them and how to find interesting elements in this elliptical algebra in particular, and how to find the corresponding links in T2 or thickened T2, which correspond to these interesting elements of elliptical algebra. So I'll try to talk about that. And then the main goal of this paper and of this talk is to categorify this theorem of Morton Samuelson, or at least like show a direction how this could be categorified. So the natural categorification of the scale algebra, or at least the possible categorification of the skein algebra, is this trace of affine Hecke category that I will define later in the talk. So there is a affine Hecke category related to affine circuit bimodules. And then you take this trace construction that we heard in Ina's talk, and I'll try to outline what this means. So that would be kind of a model for categorification of the left-hand side. And then I'll talk like what you expect on the right-hand side. Again, you need both parameters now visible, and there is some categorification going on. And like what could be a statement relating these two categorical structures. And we partially answer this question in the paper. So that's the plan. Okay. But for now, I want to talk just about some algebra, like what is elliptical algebra, how to think about it, what are generators and relations and all that. And so the first definition of elliptical algebra, that's interesting. Sorry, my internet is getting slow. Fine, was given by Bourbon and Shipman about, I guess, 10, 15 years ago. So this is an algebra A, and it has generators which are denoted by P and N, where M and N are arbitrary integers. Mostly we will focus on the case when N is positive, but M is arbitrary. And so if you like topology, you should think that P and N, at least if M and N are coprime, this is just a torus node that you draw on the torus. So in the skein algebra, P and N is just a generator corresponding to the torus node Mn. If M and N are not coprime, you have to be a bit more careful. And this condition that n is positive means that the torus knot kind of is oriented in positive direction in some way. And then there are relations. So there are lots of relations in the algebra, and I certainly don't want to write all of them, and I don't want to write maybe specific ones because we won't need this today. But there is one particular relation which is kind of the most interesting one, and then there are even more complicated ones. So you take this generator Pmn, and you take another generator Pm prime and prime, and so you can draw this triangle with vector Mn, another vector M prime and prime, and the third side would be the sum of these two vectors M plus n prime and N plus n prime. And so assume that this triangle has no integer points except for the vertices. So no integer points on the sides and no integer points in the middle. So this means that the area of this triangle is 1/2. And so if the area of this triangle is 1/2, then actually the commutator of this arrow, Pmn corresponding to this arrow and Pm prime and prime corresponding to this arrow, up to some coefficient is just Pm prime, N plus n prime and N plus n prime here. So this is a pretty special relation, which really sees how these vectors are positioned on the integer lattice. And it's clear that in particular, because there are no integer points, M and N should be coprime, M prime and prime should be coprime, M plus n prime and N plus n prime should be coprime. And again, there are no integer points inside, meaning that the determinant of Mn, M prime and prime is equal to plus minus 1. And so if this is satisfied, we have this commutation relation. If there are integer points on one side of the triangle, there are more complicated relations, which I'm not going to talk about. And if the vectors are collinear, they actually commute if they point in the same direction. But there are just more relations of this kind, which kind of capture how these vectors Pmn and prime are on the lattice. And this coefficient depends on Q and T we won't need the explicit formula, but this is some rational function on Q and T. Okay, and so one thing which is kind of clear from this description is that there is an interesting action of SL2Z. Maybe I should write it down. So there is an action of SL2Z on this algebra by automorphisms. Strictly speaking, it's a universal cover of SL2Z, which just rotates these vectors. Because this condition that there are no integer points inside is on the boundary, it's invariant under the action of SL2Z, so that works. And then all other conditions are also of this type, so that they will be also satisfied, model some technical difficulties. And so you have an interesting group of automorphisms. And again, if you like topology, it's not surprising because on the torus, you have a mapping class group, which is SL2Z, and it acts on the skein algebra by automorphisms as well. So at least that matches. So what do we know in general about the algebra? So some facts. So the first fact is that if T is equal to Q inverse, if we really specialize to this case, then the relations simplify dramatically, and all for any triangle, you have that commutator of Pmn and Pm prime and prime is proportional to Pm plus n prime and plus n prime, up to some factor which depends on the determinant between M and N and M prime and prime. And this is true for any triangle. And so you can just, so what Morton and Samuelson did, they basically said that, well, you have this specialization of elliptical algebra, forget about the general definition, and then prove that, first of all, the elements of the skein algebra corresponding to torus knots satisfy this equation. And somehow there are no other relations, which is a harder thing to prove. But this is kind of a version of skein relation, which is non-trivial because of this power D, but again, it's essentially a consequence of many, many, many skein relations in the torus. For general QNT, what can you say? So important thing, which will be kind of important for us, is that this positive part of this elliptical algebra has a basis. So we want to understand the size of this algebra if we want to match it to some kind of skein. And so for any QNT, the algebra has a PBW basis, Pankregarkov width basis, and the basis is given by convex paths. So you imagine that you have PM1 and 1, PM2 and 2, and so on. And then you have a composition of these P's, and they're arranged in the convex path so that the slopes are increasing. And basically, that's actually quite non-trivial statement proven by Berman and Schiffman. Morally, you just kind of, whenever you see two vectors, if they're not convex, you can replace them by convex by commutator relations. But because commutator relations are so tricky, it's actually a very subtle statement. But you do have a basis. And as a corollary, you can compute kind of the size of the algebra. You can find like how big it is, because what's the dimension of this algebra in by degree Mn. So the algebra is bigraded. And if we look at by degree Mn, we just look at the number of all possible convex paths from the origin to this point Mn. Write this down. So this goes from 0, 0. This is the point Mn. And then the number of ways to break the vector Mn is the sum of vectors M1 and 1, M2 and 2, up to Mk and k. The number of these summands is not fixed. All these n's are positive. All these m's could be positive or negative. And then the sum of m's is equal to m, the sum of n's is equal to n. And again, you can check that the number of convex paths from the origin to Mn is the same as the number of such decompositions up to permutations of some n's, because again, if we just look at the degrees, if you have a non-convex piece, you can kind of change the order, and then it becomes convex. Okay. And,
initially, you said that only one index is positive. Are you saying now that both indices must be positive?
No. N is positive. Sorry, I wrote it twice, but it's the same n.
And then m's can be negative, right?
M's can be negative, yes.
So there are infinitely many such things.
Yeah, it's infinite dimensional. So I'm kind of saying the dimension, but like it's really infinite dimensional thing. Yes. But I mean, the number may be not a good thing, but you have a basis in appropriate sense of given by these compositions or by the convex path. Okay. And any element can be written as kind of finite linear combination of this convex path. So that's PBW theorem, basically. Okay. In particular, like one element you can also say that there is some kind of filtration by the number of steps in here, and that's kind of a bit more finite, but still infinite. So it's complicated. So if you have just one step vector, well, there is only one vector from 0, 0 to Mn. If there are two steps already, you have infinitely many choices for how to draw this convex path. So that's pretty complicated, but it is what it is. So the algebra is infinite dimensional, but it's kind of controllably infinite dimensional. Okay. And so that is this presentation with PMNs. And I think that's like the best you can get from there, that you have this basis of convex path and you have this, but the main problem with this presentation is that it's really hard to come up with some interesting elements. So if you have an element which is not PMN, well, you need to write it as some combination of PMNs, but it's kind of really hard to visualize it. And so if we want to understand this relation to skein algebra, if I want to draw some knot, maybe it's not a torus knot, well, I can kind of use skein relations to resolve it by torus knots, but maybe it's not ideal. Maybe we want more interesting elements of the skein to visualize in this setting. And so that is what the next presentation does. This is called shuffle realization. And it was considered by many people, I guess, starting from Fagin and Adesky, and then Fagin, Hoshina, Shiraishi, Yanagira, and then Schiffman Vasiroa, and then revisited and kind of filled in with many specific details which are relevant for this discussion by Andrei Niguz. And so what is this shuffle realization? So you have, for every n, you consider the space of symmetric Laurent polynomials in n variables. So these are just symmetric in Z1 through Zn, and they could depend on Q and T, and the coefficients are really rational functions in Q and T. And inside the symmetric Laurent polynomials, you consider the subspace Sn consisting of polynomials with satisfying the following conditions. So if I choose the first variable, then I take times q and then times qt. So the consecutive ratios are kind of q and t and then qt, or t and q and then qt. In both cases, the polynomial must vanish. So other variables don't care, but if you have three variables here, again, it's symmetric, so it doesn't matter which three variables related by these coefficients, then the polynomial must vanish. And so this is a subspace. This subspace, I mean, again, it's infinite dimensional, but it's fine. And we can define the so-called shuffle product on these subspaces as follows. So we have symmetric Laurent polynomials of n variables. We have another symmetric Laurent polynomial of n prime variables. And then we build a symmetric Laurent polynomial of n plus n prime variables. So that guy would live in S n plus n prime. And so what do? We apply the first polynomial to the first n variables. We apply the second polynomial to the second n prime variables, starting from n plus 1 to n plus n prime. We have some factors, some rational function in q and t and z's, which are maybe not so important. And then the claim is that the result is, first of all, is a Laurent polynomial. It's not a rational function. So all these denominators will cancel out. And one way to see this is that from this formula, you get a symmetric polynomial, symmetric rational function, and the poles when zi is equal to zj are of order at most 1. But if the function is symmetric, you need to have at least 2. And so this is really polynomial. So if it is symmetric and the poles are of order 1, then it's actually polynomial. And so this is a polynomial, and moreover, this still satisfies these will conditions, which is also a non-trivial check to do. So the theorem of all these people who are listed above in various combinations is that the shuffle product preserves this will condition. If f and g satisfy will condition, then the product also preserves. It's an associative product, and this associative algebra, which is the direct sum of all different SNs, is actually isomorphic to the positive half. So strictly speaking, positive half of the elliptical algebra, if we allow the coefficients to be rational functions in Q and T. Okay, and so this is a very non-trivial result, obviously, and I'll tell which polynomials correspond to PMNs in a second, but here n is the same n as before, so this is kind of the number of variables in this polynomial. And in particular, if you want to build some interesting elements of elliptical algebra, you can go through this isomorphism and say, hey, so here is a specific Laurent polynomial which satisfies these will conditions, then it defines me an element of S, and therefore, by this isomorphism, it defines me an element of A. And so there are many more interesting elements here than you can build by hands by combining PMNs. So that will be our main object to study. And again, you see maybe more clearly in this language than in the definition of A, that you see Q and T and QT, and everything is symmetric in Q and T in particular. So everything what I will do will be symmetric in Q and T. Okay. And so, yeah, that's what I just said. So why do we care? It's easy to find interesting elements in S, and it's hard to find interesting element in A. And so one specific thing which I want to say here is that we will be interested in the following elements. So I have a vector of integers, d1 through dn. And then I just take a monomial z1 to d1 up to zn to dn, some normalization factor, some denominator, and some extra rational functions. Doesn't really matter. And then you symmetrize in z's. And so this is a pretty complicated rational function a priori. And it can be defined for any d. And so the result of Andrei from about 10 years ago, actually, is that this RD satisfies will conditions. So it is an element in this algebra S, in the shuffle algebra, which is, as we know, isomorphic to elliptical algebra or positive half of it. And so again, this is not just a rational function. All denominators cancel out. So it is actually a Laurent polynomial. It's symmetric. and it depends on this integer vector of G's. And moreover, if we choose very specific vector of G's, then so G's are this integer part of mi over n minus m I minus 1 over n that some of you have seen before. Then for this specific vector of G's, this element Rd of the shuffle algebra matches the element, the generator Pmn of the elliptical algebra under the isomorphism. But somehow the whole point of this discussion is that there are many more Rds than just Pmns. We can vary this exponents d1 through dn arbitrarily, and they define lots of interesting elements of S. And we can study commutation relation between those, which in particular would include commutation relation between Pmns. But as we will see a bit later, like all these RDs, they correspond to some very specific links and knots in the torus, and some very specific elements of the skein algebra or categorical skein algebra. And therefore, if we understand, like we expect that relations between RDs, they kind of more easily understood on the skein side and on the categorical side, as we will discuss. Okay, and maybe one last thing from this part. Oh, yeah, let's talk about this. So what do we know about RDs? Now, what are the commutation relations between RDs? Well, there are, let me just scroll here. So they satisfy two kinds of relations, at least. So the first relation is that when I have this vector of G's, I switch di, I subtract 1 from di, and I add 1 to the next di plus 1. So you can think of G's as some kind of integral weight, and then you add the root or subtract the root. And then the difference between this and that times qt is actually 1 minus q times the product of two RDs when you break in the middle, and that should be an I. So you just break this thing in the middle and multiply by 1 minus q. And so here you see that in particular, you just have 1 minus q. You don't have 1 minus q in big power. And that is more similar to a skein relation that you might hope for. And then the second relation, which is a bit harder to prove, but which also has various geometric meanings, is that you have this big RD and you have just RK. So this would leave in S1. This is just a degree 1 element. So that would leave in Sn. That would leave in S1. And then I'll compute the commutator with respect to this shuffle product. And the commutator has tons of terms. And so the terms are a sum of sums. So I kind of move this k through this indices d1 through dn. And at every point, I compare k with di. And if k is bigger than di, I have this sum from kind of when I go from k to di, essentially. So this k minus a would go from k minus 1 to di. And then you have the sum, and then again, you keep scanning through d1 through dn, and you have all these terms coming up. And then if k is less than di, you have similar terms when you go from di to k. And so you have this giant sum here, and then that's times t minus 1. And that is a relation that you can see in the shuffle algebra. And so this was kind of known from previous work of Andrei. One thing which we proved in this paper, which was not completely obvious, but again, it's kind of combination of things which were known, is that this is a complete set of relations if we work over rational functions in Q and C. So in particular, the algebra is generated by S1, so just by products of this single element RKs. And then somehow if you impose these relations and these relations, you can recover all the relations in the shuffle algebra and in the elliptical algebra by some complicated procedures. So I'm not explaining this, but basically this is the thing that we want to work with. So you can ask, like, one thing which can be asked is that whether the commutation relation between these different RDs when you have bigger thing, and I don't know a good explanation of this. I don't know like good commutation relation, but that's an interesting question. If you have like longer RDs commute with each other. Okay, and then maybe the last remark about this part. Yeah, so if we work over integral polynomials in QNT rather than rational functions, that's actually not true. So it's not true that the algebra is generated in degree 1, and you need probably more generators and more relations if you want some kind of integral form. And so all these isomorphisms between shuffle algebra, elliptical algebra, and this just algebra with RDs and these generators and relations, they're all isomorphic over rational functions, but they give slightly different integral forms of elliptical. And so like one question that was for quantification is like, which integral form is right? And like this looks the best one for quantification by some reason, but maybe you need to add more relations to kind of fully understand what's going on if you want to work with integral forms. So I'm kind of suppressing this discussion a bit today. Okay, so that was kind of a long algebraic part of the talk. So maybe I'll pause and ask if there are any questions about this algebra. Okay. Okay. So anyway, so what we will need later is just like you have some algebra, generators are labeled by this integer sequences T's, and relations are what you see on the screen. And so that is the kind of thing that we're interested in categorifying and seeing how this works. Okay, and so for categorification, let's talk a bit of topology, although I don't have that many pictures. So we start with affine or extended affine Braid group. So extended affine Braid group is the mapping class group of the annulus with n marked points. It's generated by the standard Braid group, which permutes these points kind of locally and generated by sigma 1 through sigma n minus 1. And there is additional element omega, which takes n's point, which goes around and comes back to the first point. So sometimes people draw affine braids on this square where you have the left and right hand side identified. So you have some kind of cylindrical picture. And then in this setup, for omega, the last strand goes to the right and then it comes back in the first place. And then your sigma I are just the standard crossings in the middle of this diagram. So this will be the standard Braid diagram, and then you have omega over there. And then the relations are basically the standard Braid relations, plus these relations, which I hope I drew omega in correct direction. Otherwise, you need to invert it. So anyway, so you have omega sigma I, omega inverse is sigma I plus 1. And you extend this cyclically. So in particular, you can define an element sigma 0 by omega sigma n omega inverse. And then you have another element sigma 1. And then if you do this operation one more time, so you get omega sigma 0, omega inverse, you get back sigma 1. So somehow you can get from sigma n minus 1 or sigma n to sigma 1 in 2 steps. This is n minus 1. Okay, and so one thing which we will need in this extended affine Braid group is the following element, yi. So it's the following product. So sigma I minus 1 inverse up to sigma 1 inverse omega, sigma n minus 1 up to sigma I. And then if you don't care about this algebra, what is yi? You take ith point here and it just goes around the annulus, and then all other points stays the same. So this is the easiest way to draw this yi. Just ith point goes around and nothing else happens to other points. And then yj is equal to yji, because if you move i's point around or j's point around, this obviously commute. And so you have in the affine Braid group, you have this commuting family of braids, yi, yj. If you like affine Hecke algebras or affine symmetric group, you also have this as a quotient, but they really live in a affine Braid group and will need this. And so now, what is the general idea, which I think many people here are aware of? So we want to think about the skein of the torus so the generators of the skein of the torus are links in T2 cross 0, 1. We can rewrite T2 cross 0, 1 as the annulus, or maybe disk minus a point, doesn't matter. So this is also the annulus. cross S1. So we just specify one as one direction, and then we have another as one direction, and this interval direction, which is the thickness of the annulus. And so we can think of the links. So in other words, we have this annulus, and then we have this circular closure of the annulus by thickening it and kind of, or taking solid torus and deleting this green core of the solid torus. And so we want to draw links in this complement to this green core, or we have a link which is essentially an affine braid going around this green core, and then it closes up around this thing. And so this discussion, which I'm trying to explain, is that we, roughly speaking, identify links in this thickened torus with annular closures of affine braids. So affine braids lives in the annulus cross interval, but if you close it up, you get another circle, and that gives you a torus. So that is maybe not so surprising. Strictly speaking, not every link in this thickened torus appears this way. So all these links should kind of go in monotonically in this annular direction. But there are a lot of them, and you can study again which classes in the skein they correspond to, which classes in other things they correspond to. And somehow, if you understand these links which go positively, at least in classical skein, you need those which go negatively, and they generate the full skein algebra. But maybe that's a technical detail. So yeah, the key point is that you just look at the affine braid, which is maybe, I don't want to draw this, but you have endpoints going around an annulus cross interval, and then you take the annular closure of that. And the same way you can interpret the skein product. So you can say, well, so if you have one annulus inside another annulus, you have multiplication operation from A bar N and A bar M. So affine braid group on N strands, affine braid group on M strands. You can put one inside another and just completely disjoint annuli. You have some braid for these guys, so they permute and maybe go around. These guys permute and go around. But you have a map, and you have homomorphism from A bar N to A bar M to A bar M plus N. And then again, if you take the annular closure of these things, you recover the skein multiplication for these particular links in thickened torus. And so we will think, because we will do some kind of more algebraic construction than links in solid torus, we will just think about annular closures of affine braids, and this operation corresponding to skein multiplication. So we put one annular braid inside another. Okay. And so we want to categorize this. So we want to categorize what is affine. We want to categorize affine braid group. And we want to categorize the separation of annular closure. And that's what I'll explain on the next page. So the affine braid group is categorized in fairly standard way by the category of affine Zorgil bimodules, or complexes of those, or extended affine Zorgil bimodules to be precise. So that's a category which was defined by Mackay and Seal and revisited by Ben Elias in a very long and detailed paper. And so what is affine Zorgil bimodules? We have a ring R with variables x1 through xn, an additional variable delta. We have the standard bimodules bi, which are just R tensor R tilde times R tilde over invariance under simple reflection. And then you have the standard Rouquier complexes. I guess we need tilde here. And then you have one more guy, which corresponds to omega. So this would be a bimodule where the left action is standard and the right action is twisted by this element omega, which acts like this. So it shifts xi to xi plus 1 and xn to x1 minus delta. And so basically for each ti, we have some complex of bimodules over this ring. Doesn't really matter which one for this exposition. And then for omega, you have one extra bimodule, which is interesting, which is the new part of this construction. So, and then this is the category. So the category of affine Zorgil bimodule is just the category generated by these b's and omegas up to tensor products, direct sums, and taking direct sum ends and grading shifts. And so I think, let me refer to Elias, is that this Rouquier complexes Ti and omega, they satisfy the Braid relations in a affine Braid group up to homotopy. And so in this sense, this Ti and omega, they give a categorification of the Braid group, where Ti correspond to sigma I and omega correspond to that omega that I was talking about. And so we were interested in these commuting elements Yi, where i's point goes around, and they also lead canonically to some Rouquier complexes which commute up to homotopy. So this, by historical reasons, he is calling this Wakimoto objects in the affine Zorg category, but maybe it's not so important. And maybe a kind of remark here that if you think about it, so Yi are not positive Braid leaves of any affine permutation. So you need to be a bit more careful, but some products of Yi's are positive Braid leaves, and you can use it to build this capital Yi. So there is some technicality here, but actually doesn't matter which positive leaf to choose and so on. And so you have interest in Braid group, and you have like kind of canonical Wakimoto objects Y, which we understand. And then with the last thing which we need to do is to consider this annular closure. So these are affine braids, how to close them up in a circle. And that's a complicated thing, which I'm not going to explain well. I'm sorry about this. But we just use this operation of horizontal trace of this monoidal category. If you were to Ina's talk on Monday, she defined this quite carefully. Otherwise, the reference is Belikova. Habira, Loud, and Živković. And strictly speaking, you might want to work with the derived version of the horizontal trace, which we developed with Paul Vedrich and Matt Hogenkamp. But again, for this, you don't really need this derived version. And it just some formal construction which says how to close the braids. That's all what I want to say for now. And then the important thing is that there is a functor from this category of affine Zorg-Gilbert modules to its trace. And this is the trace functor. So for every kind of braid or affine braid, you associate an object in the trace, which is the closed affine braid, annular closure of affine braid. And again, many people in the audience know what I'm talking about, but I don't have time to define it. It's too technical. And so finally, I want to talk about the results. So now what is our goal? So we have this weird algebra, which is the version of elliptical algebra with these different generators and different relations. And then we have this category, which is familiar to many people, is that you have affine Zorg-Gilbert modules and you take the trace. And then you want to compare them somehow. And that's what we do in this paper with Andrei. That's the main result. And so the main theorem number one is that we can take the product of these y's. So we have commuting elements y, but just take the product of these y's in some powers d1 through dn. And then we multiply by additional braid, which is just a subword of the Coxeter braid. So you have the product of t1 through tn minus 1. Maybe we erase some letters, but it's really kind of a short thing, short permutation if you want. So it's T1 up to some point, then maybe you erase some letter, then you have from some Ti to some Tj and so on. And so this is a subword of this Coxeter element. And then the claim is that these guys already generate the trace of affine Zorg-Gilbert modules as a triangulated category. So any element in the stir of A as Bman can be written as some kind of cone built out of these guys, or iterated cone built out to these guys. And so in particular, if you're minus 1, if you don't erase any letters, if you just take the product of y1 d1 up to yn dn, and then you have t1 through tn minus 1, that's a knot. So this is kind of a pure braid, if you want, because yi send every I to its own position. So the product of y to the power di is some pure affine braid. and then I multiply by this braid T1 through Tn minus y, which connects all the strands. So this is really a knot that we're considering. And so we'll call this guy ED, E sub D, where D is this multi-index D1 through Dn. And then what we have here is more or less a skein product of these EDs, because when I raise letters, this is corresponding to skein product of these things. And so in some sense, you can say that the category is generated by skein products of these EDs, although you need to be very careful with like saying what is skein product, and I don't want to be. And that matches, okay, I'll say in a second what that matches to. So we have some description of the category. We actually have much smaller generating set for this trace, which is more complicated, but for some people it might be interesting. So let me just briefly mention this. So you pick affine permutations. So in a SN tilde, I don't want to define this, but you look at all conjugacy classes in a affine symmetric group. In every conjugacy class, you pick a minimal length representative and pick a positive braid lift of that. So this is some element of the braid group, and you look at the corresponding affine complex of affine circular bimodules, take the trace, and then that is enough to generate the trace. And so in this sense, if you want the kind of smaller generating set, it's sufficient to take this minimal length representative of conjugacy classes in SN tilde. And it's a great question for the audience. What are conjugacy classes in SN tilde? But the fact is that these are parameterized by convex paths. So if you remember that elliptical algebra had a basis parameterized by convex path on the plane, this is actually kind of in this language, this convex paths mesh conjugacy classes in SN tilde, and this kind of product of PMNs, they morally correspond to these things. And we can talk about this later. So in particular, if you have just omega to the m, just this element, so that has length 0. And so it definitely has minimal length in its conjugacy class. And so that corresponds to PMN. And so in this sense, we can see PMNs pretty clearly. But again, this is kind of a technical thing, and I'm happy to discuss this if anyone is interested. But less technical thing as well. So we have actually this lots of objects, E sub Ds, which correspond to these things, which we can draw as explicit affine braids or annular closures of affine braids. Basically, the first point, it goes D1 times around the annulus. The second point goes D2 times around the annulus, and so on. And then you close up to make it a knot. And then you have skein products of those. And then you want to know the relations. And so that is this theorem, which is the main theorem here, if it uploads well. So there are two types of relations. The first relation is there is a chain map from this guy to this guy. And the cone is filtered by two copies of the skein product of E d1 di minus 1 and E d1 dn. And we can write this chain map explicitly. And the more interesting relation is that we have D, a vector of D's and a single K. And so the claim is that there is a sequence of objects, G0 up to Gn, in affine circular bimodules with the following properties. So the trace of G0 is just the product of EK and ED, where K is in front of D. Trace of the last one of Gn is the skein product of ED and EK, where EK is in the back. And so kind of we want to measure the commutator of EK and ED, but instead we write this. And then there are lots of intermediate objects, and there are maps between intermediate objects which go in different directions depending on if K is bigger than Di or less than Di. So if K is bigger than Di, there is a chain map from Gi minus 1 to Gi. If K is less than Di, we have a map from Gi to Gi minus 1. And the cones are actually isomorphic to direct sum of two copies of the following thing. So they're not only filtered, they're really kind of split as two copies. Either, sorry. Yeah, that's right. Either something like this for all different A's, between K and Ti, or something like this between K and Ti. So the cones are just filtered by these things, or they're filtered by these things. And if K is equal to Gi, then actually have maps both ways, and Gi is isomorphic to Gi minus 1. Okay, and so again, we can have some explicit relations between EGs, which are of this type and of this type, where you have the cone kind of, you don't have a chain map from this guy to this guy with filter, but you have a chain map between this guy and all these intermediate steps, Gi, and these intermediate cones are filtered in controlled way that we understand. So there are kind of complicated relations. And if you remember the relation between RDs in the shuffle algebras, they match exactly. So you just replace each exact sequence here, or each cone, by just 1 minus q times something. And so these are exactly mimicking this relation between RDs on the level of K theory. And so another remark is that these exact sequences that we write here, they really categorify the usual skein relations in the skein of T2 between the corresponding links. So we really just find some crossing and apply skein relation and keep going between them. So this is a good sign, I think, for codification. One can use this to study just a purely algebraic problem. Again, maybe I'll say in words. So you have a affine Hecke algebra, and you have the classical notion of trace of affine Hecke algebra, where you have affine Hecke algebra mod the commutator, and you can find the basis in this trace of affine Hecke algebra, which was done by He and New and other people, and you can define some kind of skein product there, and this technique allows you to compute in the skein product. But I'll skip this. And then finally, the last thing which I want to say, so there are like kind of weird, complicated sequences of objects and weird, complicated exact sequences between them. Like, why do we care that much? So one motivation, and kind of the main motivation for us, was the previous paper of Andrei, when he studied exactly the same exact sequences. Sorry. In the geometric setup. So he has so-called commuting stacks. So you have a pair of matrices which commute, mod the conjugation of GLN. That's a complicated thing called commuting stack. And Andrei Good and Yu Zhao found some interest in objects in the derived category of this guy, and some maps between them, and some exact sequences and exact triangles relating these objects. And these exact sequences, they match exactly what is written here. So in particular, there are maps in correct direction between these different G's. Sorry, I don't know what's going on. Fine. And then the relations between match on the nodes. And also you can interpret, so in the original paper of Andrei, you can interpret this as some correspondences between Hilbert scheme of points on C2. So these relations and the maps are not completely random. And EGs correspond to some interesting line bundles on some Hilbert schemes. And then maybe last two remarks is that, first of all, Oblomkov and Rozansky, they have a very complicated theory, also categorifying a affine Braid group using some really tricky category of matrix factorization. And they have a link with commuting variety. And it's an interesting thing to understand what they're doing from. So find these elements EG in their setup and like try to make some computations in their setup, but I just maybe don't understand as well. And then the last thing is I want to advertise the talk of Nicole Gonzalez tomorrow because I think what she will be talking about is directly related to what's happening here, but I'll let her comment on that. And I think I'll stop here. Thank you so much.
Do we have questions?
Eugene, does the trace of the affine Zergel bimodule category act monoidally on the trace of the regular Zergel bimodule category?
That's expected, but there are lots of difficulties there. I mean, so I was kind of skipping this thing. So there is the skein product. So skein product you can define for braids because kind of it's preserved by braid relations. It's not a bifunctor, so there is no. Maybe I'll go up. Let me. Yeah. So this thing, there is no bifunctor on the level of affine Zorgel categories, as far as I know. And there are some kind of subtle homological algebra reasons why there is no such bifunctor. There is like the problem for defining the morphisms. And the same reason you can just kind of fill the hole in one of them. And so you would have an action of affine braids on usual braids. But as far as I know, that's not categorified yet because there are some homological algebra issues. And the same reason you would expect some kind of flattening functor from affine braids to finite braids by filling the hole. And again, that is not known and that's not constructed. So there is a lot of things to be done here, but yeah, the expectation is that maybe you need to kind of slightly change the category and make it slightly more derived, but you would have the sections. But again, like when I was talking about the skein products, I just like defined this object as a skein product of braids, but formal definition is this. And then we just work with this formal object and then prove this exact sequences within this. But it's kind of a subtle equation of defining skein multiplication in this categorical setup and acting on finite skein on finite Zorgel categories. Yes.
Thank you.
Sergey?
Yeah, thanks for a very nice talk, Eugene. So I have a question about Homfly versus the finite rank. So last year, there was an interesting paper by Kato and others, Makedonsky, I think, and I forget the other co-author, who categorified Daha at finite rank. So if they take, for example, stable limit, would they recover your structure, or is it missing some part of structure? What's the relation?
That's a very interesting question, but so I don't know. I mean, so this is related to Daha, first of all. So this is related to spherical Daha at infinite rank.
Yeah, that's
yeah, but like, I don't know how, like, I mean, it's a very good question how their constructions relate to all this. I don't know, but
they also seem to work in a derived setting. So on the face of it, it seems that maybe just taking stable limit will coincide.
No, it's like, yeah, I mean, probably it's related, but I can't comment on this. Yeah. Somehow the codification that many people, including like Shipman and Vassaro and their collaborators, considered is this commuting stack. So you just like formally define this coherent sheaves and commuting stack, or maybe some subcategory of this. And so you can define it, you can define some kind of categorical convolution product on this. And on the level of K-theory, you get back the elliptical algebra by the results, but somehow it's really hard to compute, and somehow the shuffle realization is just a different way to compute there. So, and that's one point. So like Nigood and his student Yu Zhao, they have like a big program of like actually categorifying from this perspective the elliptical algebra. And so I think you had like very nice results in this direction.
Okay, so I have similar question about what is known on the other side of the Morton-Samuelson theorem in categorification of this elliptical algebra from the side of the algebraic definition.
I'm not sure I understand the question. So the categorification from the side of algebraic definition is precisely this. Okay, sorry, my screen just blanked. Is this like derived category of commuting stack? I think like that's kind of an algebraic side it is. But you can ask like then what are kind of generators and relations, and kind of is there some kind of diagrammatic codification? And again, there are some like there are some algebraic constructions here, especially in the work of Zhao, which says that, well, you have some objects and then you have kind of scaling products of these objects and you have some relations between them and some morphisms. But again, it's not, as far as I know, it's not kind of full algebraic categorification. So there is a lot of work to be done. But like there are some, like you can define some relations and you can find some kind of categorical versions of these relations. So this is kind of a weak version of categorification if you want. And like full categorification in style that like many people here would like is still not done as far as I know.
I have a question. So is it some kind of mirror symmetry because you have coherent shifts on one side and some topological thing on the other side?
I don't know. I think Ben Cooper is here, so he might say something.
Ben, do you want to say something?
I'm sorry, I missed the question. Could you repeat?
Do you understand the mirror symmetry interpretation of this Morton-Samuelson theorem?
There is an interpretation in the paper that I wrote with him. There still needs, there's some basis argument that's left to prove, but essentially our result ends up being the Legendrian skein algebra, not the full Homfley skein algebra that's in his paper with Morton and so there's some conjecture about how to obtain the skein algebras associated to quantum groups in the Homfley PT skein algebra, but you know, using Fukaya categories. But this is not published at all. Does that help?
Yeah, I think so. So yeah, I mean, like if you're interested in mirror symmetry interpretation, I think you should look at Ben and Peter's paper. So they have some Fukaya category interpretation of skein algebras. Let me repeat this. Marco?
So, hi, Eugene. So thanks for a nice talk. And well, I have two, well, 1.5 more naive questions. So first, in this your algebra setting where you have these two relations for R polynomials, and they look very nice. I mean, some of the things also, well, it's not quite, but can you have some diagrammatics for that in a sense, like, you know, for quantum SL2 or something like that? First of all, you mentioned this, like you have weight or something like that, but in some sense you really split. So this first relation looks, I mean, do you have any diagrammatic interpretation, or can you write it somehow in some nice way? So many of these formulas are very similar to, well, even old Aaron stuff with SL2 or quantum SL2, but not similar, but you have that flavor, these kind of summations and this kind of, well, okay.
Yeah, I don't know. I mean,
just wondering, I remember a long time, well, this is from your older paper, right? These relations are from...
This is from Andrei's older paper, I guess.
Okay. So I remember seeing them a long time ago, but I don't know if there is some nice, well, you know, like if you think about KLR, it's hard if you write it like something complicated. Like purely algebraically, it seems complicated, but you can write some diagrams, and I'm just wondering if...
Yeah, I mean, I don't know, but I think like this is the maybe a starting point for some diagrammatics, but again, I'm not an expert in diagrammatics myself, so I don't know. But like, I think like one important point which I want to emphasize about these relations, as opposed to kind of elliptical algebra relations. So for elliptical algebra, you have really high powers of Q and T, and like really weird rational functions. And here you have just everything is linear in Q and T essentially.
Oh, yeah. Relations are great. I mean,
and then like, I mean, that's what you want for the skein, because for the skein, you just want like 1 minus Q or 1 minus T, and like.
Yeah, everything looks perfect. I'm just wondering, since these are skein relations and it looks like these algebra, just is there some diagrammatics in this? Okay, and that is maybe comment, or maybe I missed. So the main theorem is working for T equal Q inverse, right?
No, the main theorem is like the main The theorem of Morton-Samuelson is over T is equal to Q inverse. I mean, this is like fully categorical stuff.
Yeah.
Like you have maps and then.
Yeah, but is something special in this categorification yours for T equal Q inverse?
Yeah, if you go to K tier, you basically specialize T to Q inverse. Yeah, so if you go to K tier, this chain map, this relation becomes that like this minus this is equal to like 1 minus Q times this, basically.
Yeah, but it works in the whole generality, right? For all any.
Yeah, but like you actually have maps. So like, I mean, one thing which we wanted to understand is like, if we can construct actual maps between them, if we can like figure out the direction of the maps and the cones and how they compose. So, I mean, like one thing which is kind of subtle for diagrammatics is that these all correspond to braids and kind of skein relation between braids. And usually diagrammatics is done for webs. And so you can ask if there is some kind of web version for these guys. That's a very good question. I don't know, but again, there are many experts in the audience who know much better. But yeah, I mean, at least like we're happy that you have these maps, they go in the right direction and you have correct cones and everything's fine.
Right.
And so, and if you have complicated braid, you can kind of imagine that you start conjugating it and get into nice form like this, or using maybe some skein relations and resolving by this. So this is like, yeah, this is not that hard actually, but yeah.
Okay.
Okay, thanks. Great.
Thank you.
Maybe one more comment about this diagrammatics. So you can ask the same question about finite Hecke category. So suppose that you have just finite braid group. Then a theorem which goes back to Turaev says that you can generate the skein of the annulus by products of this kind of subwords of these things, right? By subwords of this Coxeter braid. So this means that you have kind of some number of strands. You have one strand which goes across them, and then you have skein product of this. And so this is precisely the same as subword of these T's.